Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 66, and this problem asks us to synthesize each of these compounds from toluene, and this is what toluene looks like. Toluene is just a benzene ring with a methyl group on it. It tells us that we can use any organic or inorganic reagent, no restrictions apply. So let's start with A. So in A, let's just draw this out so it's more clear. So A, we have something that looks like this. So what we need to do is add a carbon, and then we need to add some sort of nucleophilic oxygen to that. So then this carbon should actually be an electrophile. So we're starting off with toluene already. So we already have the carbon that we need here. So what we need to do is make this carbon into electrophile, because then we would be adding on this oxygen, which obviously is going to be the nucleophile because it's electron rich and electronegativity properties. So we need to add a halide, for example, bromine, onto this benzylic carbon. We know how to do that. Well, through a radical mechanism by adding Br2 and light. So this adds, through a radical mechanism, bromine onto that benzylic or alpha carbon here. So now we can have an SN2 reaction occurring on this primary carbon with this tert butoxide molecule that looks like this. Let's say it's just potassium tert butoxide. Then we have SN2 kicking off your leaving group to now form your final product, which is A. What about B? So let's draw B out just so we can visualize this better. So B, we have a benzene with an aldehyde. So we're starting with something that has a carbon here. So we need to make this carbon gain an oxygen, and then we should oxidize this oxygen to the aldehyde stage and not all the way to the carboxylic acid. So we know that, for example, if I start with this product here, this bromine, I can, instead of having this tert butoxide as my nucleophile, I can just have an OH minus as my nucleophile, keying off this bromine, then I'll have an alcohol, and then I can use an oxidizing agent to oxidize it to the aldehyde stage. So let's do that. So I'll start off with my toluene. Just like in A, I'll add my Br2, my nu, light, which is a radical initiator, to get bromination at the benzylic carbon. And then I'll add OH minus to act as my nucleophile to kick off that bromine through SN2. And now I have the right number of carbons and I have the right number of atoms. These are just isomers to each other. What I need to do is oxidize this to the aldehyde stage. So if I use KMNO4, I would fully oxidize this to carboxylic acid, but I do not want to go to the carboxylic acid stage. So I need to use a weaker oxidizing agent like PCC that stops at the aldehyde stage. And now I have my product B. So what about C? So in C, I have a carbon here, which I can oxidize with KMNO4 to get this group, and then I have a chlorine that's ortho to it. But I know if I oxidize this first, then that's going to be electron withdrawing, so it's going to be meta-directing to these two carbons, but I don't want that. So I should first add the chlorine, which is ortho, which I know methyl groups are ortho and para-directing, and then I can oxidize the methyl to this carboxylic acid. So let's do this. So I have this methyl group, and then I'm going to add my chlorine to it, Cl2, FeCl3. And I'm going to get two isomers, one ortho-derived and one para-derived, plus para. And I'm only interested in this ortho, so I'll move the ortho forward and I'll oxidize my methyl group using KMnO4, which will fully oxidize all the way to the carboxylic acid stage. Just like this. So what about D? Let's see. So D we're starting off with a carbon, so this is going to be our carbon, and we know this carbon is going to be ortho and para directing. And then after we have that, after we add the nitro groups, then we can oxidize this to the carboxylic acid. So it's pretty straightforward as well for D. So let's do D. So it actually helps out a lot that we're already starting off with toluene, not benzene, because I would add one step to each of these problems. So we need to do this in essential steps. So what we got to do is that sequentially we got to first add our HNO3, H2SO4, and then sequentially we can add it to the ortho and para position. So the first time, let's just say we add it to the ortho position. That actually helps us. Why? Because now this is meta-directing, which is this carbon, and this is also para-directing, which is this carbon. So then we'll have double force being activated at this carbon. So then if I add in the HNO3 with H2SO4 again, it's more likely it's going to hit the para position. NO2, and then there's going to be an NO2 here. And also this is the plus the para isomer for this step, but we'll move on forward with only the ortho isomer. Now that we add both the NO2s, the nitros, now we can oxidize this methyl to carboxylic acid using KMnO4. And this is D. So what about E? So E, we have, let's see, so we have a carbon, and then ortho to that we have this acyl group, and then paired to that we have a bromine group. So what we can do is, let's see, so we know that we're starting off with this carbon, so we can add, for example, this acyl group first, and then once we add this acyl group, not only is this methyl group directing para, but now this acyl group is going to be directing meta, which is also going to be this position. So when we double force at this position, then we can brominate it, and then afterwards we can go through part B to make this alcohol group at the very end over here on this carbon, just like that. So let's begin. So we'll do E over here. So we'll start with toluene, and then we'll add our Friedel-Crafts acylation. 1, 2, 3, 4. 1, 2, 3, 4. AlCl3. And I will get 2 isomers. 1 the ortho. 1, 2, 3, 4. 1 the para. One, 2, 3, 4. And then we'll move forward with this ortho substitute. And the reason for that is, well, this methyl group directs here and here, the ortho and para position, while this ketone will direct para, which is also here and here. So we can doubly substitute for this we have double directing for this carbon, so then we can add our bromine. We can add our bromine with our Lewis acid. And we'll get this isomer plus the other isomer over here, which we're not really interested in. Then we'll move forward with this isomer and do the same steps in B to generate an alcohol on this methyl group. So we'll add bromine with our radical initiator. And then we'll add a nucleophile being OH minus to do SN2 and yield our product of interest. And that yields our product E. So now for F and G, we'll move on to the next page. So let's start with F. So in F, what do we have here? So in F, we have the methyl group. Methyl directs ortho and para. Then we have this amine, and we don't know how to add an amine on quite yet, but we know how to add a nitro group, and then we can reduce that nitro to this amine. And then we have another straight chain carbon here, but remember, if I had this using Friedel-Crafts alkylation, then this primary carbocation that would be on this carbon would most likely do a 1,2 hydride shift to make a secondary carbocation. So it's better if I added this as an acyl group and then reduce that down later. So in this case, it makes more sense to add your acyl group first, because then the acyl group will be meta-directing, so it would direct here and here, and this methyl group would also be ortho-directing here and here, and because the para position is already occupied, then is less chance for multiple side products. So let's add first thing this acyl group, then we'll add the nitro, and then we'll reduce them sequentially. So let's add our Friedel-Crafts acylations. We have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. AlCl3. 1, 2, 3. Oh, sorry, it's only 4 carbons. That's going to give us 2 products, one ortho substituted with one para substituted. And we were only interested in the para substituted. But now the acyl group will direct meta here and here, and then the methyl group will also direct ortho, which is here and here. So then we have double directing effects there. These carbons here, and they're identical because of the internal plane of symmetry. So all we need to do is very simply just add our HNO3 and H2SO4, sorry. And now we get our nitro group. And then we have our acyl group. And now we can reduce these one at a time. So first, we'll just arbitrarily choose to reduce. Let's say we'll reduce the acyl first, so we can add hydrazine, so that's NH2, NH2 with base. So that's 1, and then second step, we'll add hydrogen on palladium carbon. That'll reduce the nitro. And then this will give us our final product that looks something like this. So last but definitely not least, we have G. So G, we start off with a carbon, and similarly, I think that this carbon should be the toluene carbon that we start off with, because then we can add the bromine using the radical initiator, and then we can change that bromine to an alcohol, then we can oxidize that using PCC to the aldehyde, and then we can use Friedel-Crafts acylation to add this, and then Cl2 and Fe3 to add this. Because remember, the carbon, the methyl is going to be ortho and meta and para-directing, so this would be pretty simple to do as well. So for G, we'll start off with toluene. And then first, let's add our acyl group. So we have 1, 2, 3, 4 carbons, and we have Al, Cl3. And remember, we're going to get 2 isomers, one ortho and one para. And now the reason we added this acyl group first is because the acyl group is going to be directing meta to these 2 carbons, and then the methyl group is going to be directing ortho also to these 2 carbons. So we have double strengthening of the directions at these 2 carbons. That both of them being equivalent doesn't really matter which one we attack, and so then we can make sure that our chlorines, FeCl3, let me redraw that, FeCl3, the chlorine is going to attack on this carbon. And now all we need to do is add the radical initiator to brominate the benzylic carbon, which is this one. And then we need to do an SN2 using alcohol or hydroxide to do an SN2 nucleophilic attack. Switch that out for an alcohol, and then using some sort of oxidizing agent that doesn't fully oxidize all the way to carboxylic acid, only stops at aldehyde, oxidize it using PCC to get our aldehyde of interest. Which is our final product here.